Hi everyone, this is Yukabuka and welcome to my home on YouTube. In this video we continue our exploration of kobject in the Linux kernel, and this is the 6th video in a multi-part series. In one of my earlier videos I had mentioned that we needed to explore the relationship between a kset and a kobject even further. I searched online and came across this slide deck, of which this slide demonstrates graphically the relationship between a kset and a kobject. So we know that the kset has a list head item within it, and we can see that it is called list, and according to the representation here, all the kobjects that are part of a linked list are linked via this list we have. Additionally, the kset itself has a kobject value, and one of the perhaps the last kobject in this list points back at the kobject of this kset. So that seems to be the relationship between a kset and the kobjects that are part of it. Okay, let's get back to our reading material. So we'll be looking at ksets next. A kset is merely a collection of kobjects that want to be associated with each other. There is no restriction that they be of the same k-type, but be very careful if they are not. Okay, that sounds good. A kobject serves these functions. The first is that it serves as a bag containing a group of objects. A kobject can be used by the kernel to track all block devices or all PCI device drivers. Yes, that does make sense. In fact, I believe that there is a kobject corresponding to all character devices as well, and we will look at this in detail as we explore device driver models in a future video. A kset is also a subdirectory in the sysfs where the associated kobjects with the kset can show up. Every kset contains a kobject which can be set up to be the point of other kobjects. Okay. Which can be set up to be the parent of other kobjects. Yes. The top level directories of the sysfs hierarchy are created in this way. We did see this part as we were reading through the source of kobject_add. We noticed that if the parent were not set, then the parent of a kobject would be the kobject inside the kset it belongs to. We did see that while reading through the source code in an earlier video. Okay. And the third use of ksets is that ksets can support hot plugging of kobjects and influence how events are reported to user space. Yes, we did see this while reading the source as well. We saw how kobjects use the netlink subsystem to send a buffer of key value pairs to user space. In object-oriented terms, kset is a top-level container class. Ksets contain their own kobject, but that kobject is managed by the kset code and should not be manipulated by another user. That makes sense. A kset keeps its children in a standard kernel linked list. right? We saw that just a few minutes ago. K-objects point back to their containing kset via their kset field. Got it. So that makes sense. Also, that implies that every k-object is part of exactly one kset. Because if we look at source insight and go to kobject, we can see that there is a pointer to a kset, a single pointer. So every k-object is only part of one kset. K-objects point back to their kset. In almost all cases, the k-objects belonging to a kset have that kset in their parent. Right. I guess this is how. I guess this means that when kobject underscore add is called, in a lot of cases the parent field is set to null, so that it's eventually set to the kobject inside the kset it belongs to. I think that is what they're referring to over here. The next paragraph says, as a kset contains a kobject within it, it should always be dynamically created and never declared statically or on the stack. Interesting. To create a new kset, use the following function: kset create and add. Got it. So let's take a quick look at this function. Okay, we see that it's inside kobject.c as well. And if you take a look at that, it does return a kset value, and that kset is returned, or it's allocated inside kset underscore create. The arguments to the kset are the name of the kset uEvent ops, and the kobject. And the kset uEvent ops is what has the release function pointer that we saw in a previous video. Let's take a quick look at the comment for this function. It says that this function creates a kset structure dynamically and registers it with sysfs. When you are finished with the structure, call kset unregister and the structure will be dynamically freed when it is no longer used. If kset was not able to be created, null will be returned. Makes sense? Again, the idea is that you should not free the kset, but use kset unregister, which will free it free its memory when the time is appropriate. Okay, so we see that into kset create we pass name, uEvent ops, and parent kobj, the same three arguments that came into this function. And after that, there is a kset register, which according to the comment registers the kset with sysfs. It's interesting to see that it does not. If it fails, we just do a k-free. Okay, so it's probably allocated using kmalloc. So these are the two functions that we need to look at. Let's jump into this definition and let's quickly look at the documentation string. This function creates a kset structure dynamically. This structure can then be registered with the system and show up in sysfs with a call to kset register. When you're finished with this structure, if kset register has been called, call kset unregister and the structure will be dynamically freed when it's no longer used. Okay, it seems to have a very similar It's a very similar comment message as the earlier function. So we see that it's being allocated here. We see that its name is being set here. The uEvent ops are being set here. The parent is set to parent kobj, right, which is an argument to the function. Okay. The kobj's ktype is set to kset ktype, and the kset of the kobj itself is set to null. Interesting. So there are a couple of things we need to look at. We need to look at what kobject set name, or how it works. Okay, I believe we have seen this function before, kobject set name vargs. So we will not dive into that again. All it does is set the name for the kobject. So that makes sense. It is worth noting though that the name is set for the kobject and not the kset. Right. The next thing we need to know is, what is kset underscore ktype? That seems to be a structure of type kobj underscore type, and has sysfs ops and release set to a very specific address. So let's jump here and see what this is about. This seems to be a table of function pointers which have store and show, right? So these are the functions that are called when something is either written to an attribute file in sysfs or something is read from the attribute file in sysfs. That's what happens. We can dive into this and look at what those functions do, but they probably are just returning a value and storing a value. So in this case we can see that what the function does is, using the kobject attribute, using the attribute, they find the container structure, that is kobject attribute, and then they call the kattr arrow show method, which should return the value of that specific attribute file. And store should do something very similar, except in the reverse order. We get the kobj underscore attribute type from attribute, and then call the store method, storing the value that has been passed in from user space. So that makes sense. So what's happening here though? The ktype of the kobject of the kset is being set to something specific. Something curious is, yes, so the ktype of the kobject inside the kset is being set to the specific static structure. It also has a kset release function, which does a kfree on the kset. Okay. Interesting. So at this point, kset create is what the function does is it allocates space for kset, and it sets the various attributes inside that allocated structure. It's not doing any specific sysfs registration. However, it did set its ktype to a static array with sysfs ops set. Okay. So if we go back and look at kset register, we see that what the function does is it calls an init on the kset, at which point the kobject is initialized. So we need to look at that function specifically. Yes, so the kobject inside the kset is initialized. The list head inside the kset is initialized, and the spin lock inside the kset is also initialized. I am curious about how the spin lock is initialized. Let's take a really quick look, and if it's let's see. So there is a spin lock check, and there is another function that is called with the rlock that is inside the spin lock. And yes, at this point I am not going to go further down this rabbit hole. However, it might be an interesting idea to do a deep dive on the different kinds of locks that are present, maybe some other time. Okay, so kset init makes sense. The next one is kobject add internal of &k arrow kobj, and what that does is, let's take a look. What this function does is it takes the kobject inside the kset as an argument, and if the name is not set, it returns an error. Join kset if set. Use it as a parent if we do not already have one. If I remember correctly, the kobject's kset pointer was set to null. We can take a really quick look. We go inside this function, and we can see that the kobject.kset was set to null. So that if loop should most definitely, in this case we won't be getting inside that loop, and parent is set to kobject get kobject arrow parent. So let's see, this is a bit confusing. Let me just check something real quick. Okay, set create. Yes, I'm going to lock this context window and go back, go to register, and go to add internal. So inside add internal, the value being checked is a kobject get of kobject arrow parent, and kobject arrow get is, yes, it gets it increments the reference count on the parent kobject. Okay, that makes sense. However, as you can see, the kobject arrow kset is not set, so we won't be getting inside this loop here, this if block here. If we did get in though, we would have called a kobject kset join of kobject, and a kobject arrow parent is equal to parent. Right, okay. I guess that there is a different possible code path for entering this function, where the kobject arrow kset might actually be set. We have a print k message, and over here there is the create dir, which I think causes the creation of a sysfs create dir. Yes, we have seen this function before. And if there's an error, there's a bit of cleanup that happens, and else you just say kobject arrow state in sysfs equals 1. Right, that sounds good. At this point, I think we might have seen this function before, and that it's just that I don't remember. I think kobject add internal is also called from kobject underscore add, because this does look a bit familiar now. Okay, let's just go back. And there is also a kobject uEvent function. Okay, so I believe we have seen this function as well. We know how it passes a event notification into user space, so we won't look into that again. So that's effectively what it does. It creates the kset, and it creates a directory in sysfs and registers itself with the sysfs file system. So that's what create and add does. Now the next note says that when you're done with the kset, you can call void kset unregister kset to destroy it. This removes the kset from sysfs and decrements its reference count. When the reference count goes to 0, the kset will be released. Because other references to the kset might still exist, the release may happen after kset underscore register returns. The release may happen after kset underscore unregister happens. Right. An example of using a kset can be seen in samples kobject kset-example.c file in the kernel tree. So let's see if we have this file here. I don't suspect we do, because I only have the files that are indexed by cscope when building an ARM kernel. So as a result, I don't have this file on. Let's look at it in Elixir. The file name is samples kobject kset-example.c. What? Sorry. It's samples kobject example.c. Is that the one? It's kset-example.c. Okay, so in this case they have a few examples on how to use the kobject properly, including adding sysfs entries and all of that. Very nice. Okay. If kset wishes to control the uEvent operations of the kobjects associated with it, it can use the kset event ops to handle it. Right, we did see this earlier. So filter is a function that is called, and based on the results, it's decided whether the event needs to be passed to user space or not. Name is the, I wonder, is it the name of the, well, I'm not quite sure if it does this return the name of the kobject. I don't recall. uEvent is also a function pointer. Was this the function pointer that eventually sent the content to user space? Perhaps, I'm not too sure. The filter function allows for the kset to prevent a uEvent from being emitted to user space. Yes, we did see that. The name function will allow the override of the default name of the case set that user space sends, that uEvent sends to user space. Got it. By default, the name will be the same as the case set itself, but with this function, you can override that name. Right. The uEvent function will be called when the uEvent is about to be sent to user space to allow more environment variables to be added to the uEvent. Yes, yes, I do recall seeing this in the earlier video. After a certain set of environment, so we discussed this as the two ways in which environment variables can be added to the uEvent. One was by passing those one was by passing those key value pairs into the function, and the second was by setting the uEvent, setting the environment variables in a function and setting that function address in the ksets kset uEvent ops.uEvent. All right, that makes sense. One might ask how exactly a kobject is added to a kset, given that no functions which perform this function have been presented. Well, we did look at the source and we did see how a kobject is being added to the kset. Right. The answer is that this task is handled by kobject_add. When a kobject is passed to kobject_add, its kset member should point to the kset to which the kobject will belong. Got it. kobject_add will do the rest. Perfect. The last line is, if there is a kobject belonging to a kset and has no parent kobject set, it will be added to the ksets directory. I don't get that. If a kobject belonging to a kset has no parent kobject set, it will be added to the ksets directory. Interesting. Not all members of the kset do necessarily live in the ksets directory. I see. If an explicit parent kobject is assigned before the kobject is added, the kobject is registered with the kset but added below the parent kobject. Okay, so this is a detail that I don't specifically understand. It has to do with the hierarchy of sysfs and about where a kobject will be present. What it's saying is that if a parent has been assigned before the kobject is added, the kobject is registered with the kset but added below the parent kobject. Okay, got it. Okay, that makes sense. So it's just that there are different ways in which the sysfs hierarchy shows the kobject. If a directory contains a kobject on within itself, if a sysfs directory has another file within it, then it may either be because the kobject is within the kset of the directory, or that the kobject has its parent set to another kobject which is related to the directory. That makes sense. Okay, so we are almost done with our kobject documentation, so let's go through this as well. In this section we will talk about kobject removal. After kobject has been registered with the kobject core successfully, it must be cleaned up when the code is finished with it. Okay, to do that, call kobject_put. Okay, by doing this, the kobject core will automatically clean up all of the memory allocated for the kobject. Right. That makes sense. If a kobject add event has been sent for the object, a corresponding kobject remove event will be sent, and any other sysfs housekeeping will be handled for the caller properly. Yes, we did see this as a comment earlier, mentioning that if a kobject add event is being sent, then a kobject remove event will also be automatically sent later on. If all you need is a two-stage delete of the object, say you are not allowed to sleep when you need to destroy the object, then call kobject_del, which will unregister the kobject from sysfs. This makes the kobject invisible but is not cleaned up, and the reference count of the object is still the same. Right. So calling kobject_del just makes the sysfs makes the file corresponding to the kobject invisible within sysfs. It does not do any sort of reference count decrementing or object deletion. And at a later time, call kobject_put to finish the cleanup of the memory associated with the object. Sure, makes sense. And lastly, kobject_del can be used to drop the reference to the parent object if circular references are constructed. It is valid in some cases that a parent object references a child. Circular references must be broken with an explicit call to kobject_del so that release functions will be called and the objects in the former circle release each other. Right, I'm not sure of what exactly this means, because I don't see why there should be a circular reference in something that is arranged as a clear directory structure. Yeah, but it's hard to say in what case they consider this to be valid without a proper example. Okay, so in this video, in this series of videos, we've gone through the basics of kobjects, about why we need it, about how we can use kobjects and embed them in the structures that we use, about how kobjects can be initialized, about how ksets send events to user space, about how kobjects perform reference counting, about how kobjects can be created and added, and how sysfs directories corresponding to the kobject files are created, what k-types and their release methods do, what ksets are, and how kobject removal works. I hope this has been an interesting set of videos. Click like and subscribe if you are interested in similar content, because there will be more in the future.